In the data warehouse implementation section, we're going to talk about some of the computational aspects related to data warehouse. So we know that a data cube is a lattice of cuboids. We know there is a base cuboids that includes all the data, and all the other cuboids can be created from the base cuboid using different group bys. So how many cuboids is in that lattice? If we consider that each dimension, if the cube has n dimension, and every dimension has different levels, this levels refers to the concept hierarchy. The answer is this number. This is a product of the number of levels of each dimension plus 1, because each of the level could occur, and this dimension could also not occur within a cuboid. So this is how we compute the total number of cuboids. As you can tell, this involves the product of many numbers greater than 1, so this t can be a very big number. Earlier, we have mentioned that in order to support quick OLAP operations, it would be ideal if we could materialize the entire data cube. So not only the base cuboids that is already there in the data cube, but also all the lower dimensional cuboids should all be created to support the efficient query. However, this big T, this number tells us that it may not be possible to materialize every cuboid within a lattice. So you have different choices. One is materialize every cuboid, and that's called full materialization. In a large data cube with many dimensions, this is rarely done. And you can also choose to not materialize any cuboids besides the base cuboids that you already have, that holds all the detailed data at the finest granularity level. This is also not really done because it will make force all the computation that supports query to be run on the fly, and that's going to be really time consuming, making the query, making the response time to query very, very long. So vast majority of the data cube and data warehouse implement partial materialization. So some of the cuboids are materialized. Some part of certain cuboids could be materialized to support query. Chapter 5 covers a number of different strategies to support partial materialization in terms what portion of what cuboids are materialized to efficiently support computation. So therefore, you can refer to chapter 5 to read more about this. The selection of which cuboids to materialize are based on the size of the cuboids, the access frequency of the data to support queries. So more details, see chapter 5. Another technical aspect, implementation aspect of data cube is about indexing. Students with background in database knows that indexing is a critical part of any relational database. This is because that we have large number of data in a table format, and we have separate tables that's related through foreign key and the primary key pairs. In order to capture um, to support faster search and to support join operations that we mentioned before, we need to create index. Indexes helps. Indexes basically is an alternative way to represent the information in our base table, so that it provides a convenient data structure to support search, aggregation, join, and other database related operations. So one of the indexing methods is Bitmap. In database systems, we call it Bitmap, but this is not new to us. We already mentioned it. This is also known as one-hot encoding. So here we have the base table, have the customer ID, region, and type. Then for each of those columns, besides the ID column for each of those dimensions, that we can create separate index files. So the index for region going to have columns generated based on the unique values this column has. So whether it's Asia, Europe, America. The first record is Asia, so Asia has a value of 1. It's not Europe or American, therefore they have the value of 0. The second C2 is from Europe, therefore Europe column is 1 and all the rest is 0. Similarly, we can create index on type. So the retail and the dealer becomes the column. So every unique values in this column becomes the new column in our bitmap index. The advantage of bitmap index is we are encoding our information in 1 and 0s. Those are the bits, right? So 1 is true, 0 is false. In computing, bit operation is the most fast. It's the fastest. It's the most basic computation. It's just using the logic gate can find the result in milliseconds, nanoseconds. So, so for example, if we want to find which customer is from Asia and purchased through retail, we only need to end this sequence with this sequence. 1 and 1 is 1, 0 and 0 is 0. So this is true and false logical operations, very, very fast. The bitmap index typically works when we have low cardinality in the columns. We mentioned this before. So, for example, region and type, they have 3 and 2 unique values that are very suitable for create a bitmap index. Customer ID column, on the other hand, is not very suitable because that will force us to create as many columns as there is as the number of observations that we have in the original table, right? So therefore it's not cost effective. However, there are techniques being proposed that can apply bitmap on higher cardinality columns using some compression techniques. So this is about bitmap index. A second type of index, I think it's fairly unique to relational database, is because the need of join operation in relational database. Recall one of the drawbacks of snowflake schema is because it's normalized at different levels. Anytime if we need to find the real location from the fact table, we need the fact location key and match this key. This is a joint. We need to find the matching key between these two tables, join the same row there. And from that row, we will find a city key. City key still does not give us city name. So we have to find the matching city key in the city table, join this in order to find the city name and the state and the country that the city is in. So this involves two joint operations. The deeper that you normalize your relational database, the more joints is required because the table are more and more fragmented into multiple tables. Therefore, anything, any you need multiple jumps to find the raw data in the tables that's at the terminal positions. So this is why join is fundamental, because relational database is designed in that way. The table has to be normalized. Therefore, join is necessary. However, because join is very costly, so there are various indexing techniques being created to speed up this join process. This type of join index basically format the data in a more straightforward way to support join operations. So we have our sales factor table. Well, we should first make a statement to say that the join index registers joinable rows. Joinable rows, so those rows have are related to the same record from different tables, because the same event or same observation was split in across multiple tables. We need to join them back to support queries. So here what we have is our fact table. In the fact table, we have the record ID for this the rows in the fact table, but also the foreign keys that pointing to the dimension tables, remember? So here our dimensional table are location and item. And now the IDs already match, but we want to map the values. We want this join index to relate the values from the dimensions in the star schema to the joinable rows in the fact table. So from this example, what kind of index can we create? In the location table, we have some location called Main Street, and one of those 1, 2, 3 rows in the factor table are related to the location ID that's pointing to the main street. So instead of having to go through this location ID to find the main street, we can directly save this location name with the primary key of this sales table, so the ID for the sales. So from this location, between location table and the sales table, we can create this join index table. We can have Main Street because Main Street occurred are related to those 3 records. So we put the 3 primary key, the IDs, in the from the sales table here. So those 2 things are joinable because they are describing the same sale event. Similarly, we can another dimension we have is item, and there some sales involves this item, Sony TV. Again, instead of having to go to the item key to find this Sony TV, we directly create an index to put the sales key alongside with the matching item. So Sony TV was involved in those 2 sales records, and so those the rows in the sales table. Therefore, we can create a convenient index like this, mapping directly, so that when we need to query it, we don't have to go through this complex join process of matching the IDs, the primary keys between foreign key and the primary key. The similar idea, join index can is not limited to one-dimensional table and the factor table. It could cover multiple dimensional table, depending on the need of the data cube. And another point to mention, as here we have text strings, Sony TV, those are all text strings, and we can actually convert those join indexes to bitmap index to even further improve the computational efficiency. So those are the two indexing methods that can be used in data cube to improve the computational efficiency. Indexing is a fairly low level implementation details for data warehousing and relational databases. They are implemented by database engineers. When they create the tables, they also need to consider how to index the data. So it's fairly low level. More closer to the users, there is a level of processing that relates to how to efficiently processing OLAP queries. This is another element of the technical implementation details that we will cover in this chapter. So the idea is, given some materialized cuboids and a user query, the query in this case is we want to know in year 2004 which brand was sold in which provinces or state. Okay, what are given those information, what considerations that algorithms that supports OLAP query processing need to consider. So let's pretending that we are the algorithms, and we're going to see how the algorithm is going to proceed to answer this query. So first of all, let's observe that our materialized cuboids are having three dimensions. We have a time dimension, we have the item dimension, we have the location dimension. We can see in the four materialized cuboids, the time dimension is consistent at the year level. Okay, we don't have month or quarter information. But the item information are at two different levels. The concept hierarchy we have, the lower level is item name, the upper level is brand name. Okay, the third dimension, city, the location dimension, we have a concept hierarchy consists of three levels: city, province, and country. Okay. We need also to observe, keep in mind that when data is aggregated, we cannot find the finer grained data. So for example, if we have in this cuboids, we have data for country. So here we're going to have in which, for example, year of 2000, Lenovo computer has been sold in US. This table in US or Canada or China or whichever country, this cuboid will not give us any information on the cities, in which city of China this brand was sold. Okay, we won't be able to derive lower level data from a high level cuboids. Okay, that's an important observation to keep in mind. So then given this query, the system wants to find the most efficient way to get to the answer. Obviously, intuitively, we want to find one sum of the cuboids that could supply all the needed information. So we can see the first cuboid have year dimension, so we can actually use slice function. Use the slice operation to say we want to slice this and to find the year of 2004 to meet the need of the query. And item name is at a finer level, lower level than brand. So we can from item name to generalize to brand name. So this also supplies good enough information. Then lastly, city dimension. City is also at a lower level than the province or state. Therefore, from all those city information, we can generalize or roll up to province or state. So therefore, this the first cuboid is a candidate cuboid that the algorithm may select to answer this query. Now let's check the second cuboid. The second cuboid have year, brand, and country. And we can tell that year is fine. We can use again slice to match this criteria. Brand name is okay because our query asks about brand name. But country is going to be a problem, as we already mentioned. When you have the data aggregated at the country level, then we cannot find the more detailed information about province or state. So therefore, the algorithm should immediately, by using this concept hierarchy information, remove cuboid number 2 from further consideration. And we can further check cuboid 3 and cuboid 4. We will find both of them can be used to answer this query. Then the next level with 1, 3, and 4 are the remaining candidate. The algorithm will decide using which table going to give us the most fast result, the most efficient result. So in this case, the system will have to compute to know what's the size of this the first, third, and the fourth cuboid. And in this case, we need one slice, one roll up, and another roll up to meet the requirements of this query. So therefore, it can be costly. The algorithm going to compute the cost, how much of each of the roll up going to cost. The third the third and fourth seems to have simpler operation. That for the third we only need a slice to find year 2004. Brand and province are already given. So here if we use cuboid 3, we only need to do a slice year equals 2004 to find the answer to the query. If we use cuboid 4, it's already selected. The year 2004 is already being selected for us. But here we need to roll up from item name to brand name. Okay, if we have good index there to matching item names to brand names, then this number 4 can be the most efficient solution. So the algorithm could just pick number 4 and use this to answer the query. Okay, so with that, I think we have covered the 3 technical elements in data warehouse implementation. What we have done was to discuss what to materialize, to perform partial materialization, perform different indexes to support fast data retrieval, matching, aggregation operations. And we also discussed how the algorithm going to select which of the cuboids should be used to efficiently process OLAP queries. A related topic is also related to technical implementation details, but at a different level. It's at the server architecture level, is whether we want to use relational database to support OLAPs, or to use multidimensional array as a data structure. So we have discussed both earlier, and they both can be used. The advantage of relational tables, the greatest advantage is it has greater scalability, because you can have tables, and tables is a very efficient way to organize data. And also those the database management system, the backends, the existing tools, indexing mechanisms are all in place. Those are some of the advantage of using relational OLAP. But multidimensional OLAP has the drawback of using array to store data. When you have empty, a missing data, your array going to be sparse. So there's lots of empty cells. But how to store sparse data has been substantially studied, and there is no techniques to address that shortcoming. And another prominent strength as compared to relational OLAP is the array provides naturally fast indexing to pre-compute summarized data, to compute, if we recall the multidimensional array representation of a data cube, you can see the data is already aligned very well in its place. Computing their values are really efficient. We don't need a lot of complex to join operations to put data together. The data is already together. So the natural indexing, that's part of the multidimensional array, making computation of those cuboids much more efficient. So this is also the drawback. This is the strength of the multidimensional array storage. Now you can also have hybrid, right? So some part being relational, others being multidimensional. At the low level, you have relational; higher level, you have array, to get the strength of both approaches. There are also specialized SQL servers, just specialized designed to support SQL queries over star and snowflake schemas. Okay, so this concludes our discussion on the technical elements of data cube implementation and use. Next topic we're going to cover is a special technique called attribute-oriented induction.